Mitridate will talk about axion detection with collective excitation. Please, Andrea.
Thanks, Luca, and thanks to the organizer to giving me the opportunity to present this work, which I've done together with Tanner Zwitel, Kevin Zhang, and Katrin Zurek here at Caltech. So let's just start. Okay, so I don't think I have to spend too much time convincing you that the axion, by addressing at the same time both the dark matter and strong CP problem, is one of the best motivated scenario for physics beyond the standard model. And right now, the only experiment which is testing the axion parameter space is ADMX, but in the near future, a lot of other experiments will join the hunt for the axion, and hopefully we'll cover a much broader region of this parameter space. But you can notice from this figure that there is a mass window between 1 and hundreds of millielectron volt, which is not going to be tested by any of the experiments which have been proposed so far. And the main reason for that is that experiments looking for axion to photon coupling usually exploit axion resonant conversions in cavities. And if you want to do that for such an heavy axion, you will need cavities with a resonant frequency around the terahertz. And this can be done, but you will need cavities with at least one typical size of order around the millimeter. And this will give you a cavity volume which is too low to reach the QCD axion band, because remember that in out-scope searches, the signal strength scales with the volume of the cavity. So this motivated people to think about different experimental setup to test such an heavy axion. And one possibility is to go back to the standard direct detection paradigm. So you take a chunk of matter, which will be your target, and you hope that the axion flying through it will be absorbed, and this absorption will create some kind of excitations that you can detect. So the question now is, what kind of excitation should I look for? And to answer this question, you can just look at the kinematic of the process. So in an axion absorption, you will deposit an energy which corresponds to the axion mass, but at the same time, you will deposit almost zero momentum, just because the axion is highly non-relativistic. And so the excitation that you need should have a finite amount of energy corresponding to the axion mass at zero momentum. And so we identified two such excitations. They are both collective excitations. The first one are phonons. So phonons are related to vibration of the ion's lattice around its equilibrium position. And as you can see from this figure, where we are showing the phonon spectra for different materials, the typical energies of these excitations at zero momenta lie exactly in the energy window that we are looking for. So between 1 and hundreds of millielectron volt, such that this excitation can be excited by an axion absorption. The second excitation that we will discuss are minons, which instead are related to excitations of the ion spin. So in material which have a ground state with a magnetic ordering, the absorption of an axion can excite a vibration around the equilibrium position of the spins. So in the following, I will give you a brief introduction of these two kind of collective modes of the system, and I will also derive how you can estimate the rate at which an axion field would excite them, and from this we can derive constraints on the axion coupling. So let's start from phonons. And as I told you, phonons are associated with vibrations of the ion's lattice. And in one dimension, you can think to the ion's lattice just a collection of masses which are attached by elastic springs. And at equilibrium, the ions will sit at the lattice sides, but if you have an external perturbation, this perturbation can induce a small displacement. And the physics of this displacement is described by a Hamiltonian, which is just the Hamiltonian of a collection of coupled harmonic oscillators. So now you can solve for the normal modes of this Hamiltonian. And what you find is that the normal modes correspond to in-phase oscillations of the ions. which have a dispersion relation which is gapless. And this is just remembering you that these excitations are ghost-on of the broken translational symmetry. Now you can go a bit up in complexity by adding an additional ion in the primitive cell and assuming that interactions between ions in the same cell are different between compared to interactions between ions in different cells. And the Hamiltonian is still given by the Hamiltonian of a system of coupled oscillators, with the only difference that now you have two inequivalent coupling strengths. And this simple modification leads to an important change in the spectra, because now, in addition to the gapless mode, you have the appearance of a gapled mode, which corresponds to out-of-phase oscillations of the ions. And this is very important because if you remember about the absorption kinematic, you really need to couple to a mode which at zero momenta has non-vanishing energy. And this is exactly what gapled mode are giving you. Are giving you a mode which at zero momenta, which is the moment of the axion, has a non-vanishing energy. Of course, in reality, the situation is a bit more complicated. So of course, we live in 3 dimensions, and also the coupling between the ions displacement is could be more complicated than a simple nearest neighbor interaction. But the name of the game is always the same. You have to find normal modes of the Hamiltonian, and you can express then any solution, which here I call U, as a superposition of these normal modes. And if you want to quantize the system, you just have to promote the expansion of these, the coefficients of this expansion, A dagger, to operators and impose commutation relations. So standard story. And in this slide, I'm showing you the specific case of gallium arsenide. And you see that you have in total 6 modes. 3 of them are gapless and 3 of them are gap. And this follows the general rule that if you have n ions in the primitive cell, you will find 3 times n total phonon branches, 3 of which are gapless, and which are the ghost of the broken translational symmetries. So far, this is standard textbook physics. The only subtleties that we encounter in studying phonon excitation is that at very low momenta, which is the kinematic region we are interested in, you can have a non-negligible mixing between phonon and photon modes. And this is because at this low energy, these 2 modes have similar energies. Sorry, at this low momenta, these 2 modes have similar energies, and these give you a mixing between them. And these are 2 important consequences. First of all, you notice that the energies of the phonons are shift at low energy. And second of all, even if you are going to excite mostly phonon modes, they will have a small photon components in them. And as I will discuss briefly in the following, this can be very important for readout purposes. So just remember that the true physical states are called polaritons, and the one that we will excite are mostly phonon-like, but they will have a small component of photon states. Okay, so after having discussed what phonons are, let's see how an axion field can excite them. So you start from the UV Lagrangian with the usual axion to photon coupling. You can write this in the non-relativistic limit. And what this coupling is telling you is that if you have an external magnetic field, this coupling will induce an electric field. And this electric field will couple to the ions charges and lead to a coupling between the axion to the ions displacement. So now it's a simple game to express the ions displacement in terms of creation and annihilation operator and compute the rate for phonon production. And what you get is the following. So this is the rate for phonon production through axion absorption. It has quite some ingredients, so let's try to go through them. So first of all, you have the axion to phonon coupling strength. And notice that this depends on the intensity of the magnetic field. So the stronger the magnetic field, the higher the rate of phonon production you will have. Then you have the local axion field amplitude. So locally you can think to the axion as a classical field, and the amplitude of this field is given by the ratio between the axion energy density and the axion mass squared. Then you have the usual dark matter velocity integral, a sum over the final phonon states. And then you have a Brighton-Wigner distribution, which is the way in which schematize the line shape of the phonon. Of course, this is an approximation, which is reliable on resonance, but of course, if you want to make more precise prediction, you should really have a more detailed knowledge of the line shape of the phonons and expectations. Then you have this dot product, where F is just this vector which appears in the coupling, and epsilon are the polarization vector of the phonons. And the important role which is played by this piece is fixing the selection rules, which tells you to which phonon modes the axion couples to. So you will have a lot of phonon modes in your material, but you won't couple to all of them. And to which you couple to is dictated by this dot product. And finally, you have these matrices, which usually are very close to the identity, which schematize what I told you, which is the mixing between photon and phonon excitations. So if you just ignore for a moment these selection rules, you can estimate the rate for phonon production on resonance. And what you get is that for a kilogram year exposure in a 10 Tesla magnetic field, you get a very strong sensitivity to the axion to photon coupling. And this is what is shown in this picture. So we here show the constraint for a kilogram year exposure of these 4 different materials. And as you can see, by choosing thoughtfully the materials, the targets, such a way that they have complementary resonance structure, you can achieve almost broadband coverage of the axion mass in this window with just 1 year of exposure, which is quite remarkable if you think to, for example, how much time will take for an experiment like ADMX to cover almost 1 order of magnitude in axion masses. And in this picture, you can also see this peak structure, which corresponds to the resonance, the phonon resonance of this material. And so you can see that you're coupling only to a subset of the total number of gapped phonon modes in this material. And this is exactly because of the selection rules I was telling you before. Even if you have a lot of phonon modes, you won't couple to all of them. So that if you want to achieve a broadband coverage, you really need to have more than a single target. So if this is annoying in terms of achieving a broadband coverage, it gives you an handle in discriminating between signal and background, because the resonance to which you couple to depends on the orientation of the B field. So if you at some point did such an experiment and you see a signal, you can discriminate between a real axion signal and some sort of background just by changing the orientation of the B field. So if the signal disappears, changing the orientation of the B field, most likely that was an axion signal. And if it doesn't, most likely it was just some sort of background.
Andrea, can I ask a quick question? This change in the response due to the changing B field axis, this is due to the relevant orientation here is the orientation of the B field within the crystal coordinate system. It's got nothing to do with the dark matter directions or anything like this?
Yeah, it has to do with crystal structure and the selection rules with the phonon. So when you do this, this dot product, you are really taking the dot product of the direction of the B field with the phonon polarizations.
But if there was something else that excited phonons, would it not be subject to? Oh well, I guess it would have to be some photon source. As long as it's any photon source would be subject to the same selection rules, right? So are there any backgrounds that could mimic that?
Yeah, so I was thinking more to thermal noise. So if you have a thermal noise, you mismodel that changing the orientation shouldn't change the noise. Yeah.
Okay. Okay, that makes sense. Thank you.
But I think you could think to some background that also have these selection rules. Yeah.
Okay, thank you.
No problem. Okay, so, and just to be to spend some word on our topic, you can see that we are not too far from the region that the region where the Axion anomaly would live if you interpret that as an Axion signal. So if you interpret the recent Axion anomaly in terms of an Axion, solar Axion, taking into account the inverse Primakov effect, you will require Axion coupling that lives in this region, and it wouldn't be too hard to find a material which has a phonon resonance a bit higher than silicon oxide, such that you will be able to test this region and rule out or not the Axion explanation of the Axion anomaly. Okay. Of course, the constraints that I show you are obtained assuming 3 phonon excitation per year, but then there is the problem of reading them out. So you are producing these phonons in your target sample, but then you really need to take them out and read them out. And so the standard readout, which is by the mean of a calorimeter placed on the surfaces of the the target, would not work in this case, just because remember that the target is in a very strong magnetic field. So you really need to think about different readout schemes, and this will require a detailed study. We just proposed 2 possibilities that, of course, need to be studied more in detail. So a first possibility is to put a very thin layer of helium on the surfaces of the target. And so phonons will kick out one of these helium atoms, and that can be read out. The good of this, this idea is that in the literature, the efficiencies for this process is claimed to be very high, close to 1. The problem is that you need a very well-polished sample such that your phonon can pass from the detector to the helium film easily. And this is not that simple, especially for some of the materials that I showed you before. A second possibility is to use the fact that, as I told you before, the phonon that you are exciting in reality are polaritons. So even if they are mostly phonon-like, they have a small photon component in them. So you could hope that a fraction of them will decay into photon, and you can detect this photon. The problem is that we don't have right now a detailed computation to estimate the fraction of these TO phonon modes that will decay into photons. So we really need a precise estimate of this to understand how suppressed would be the signal if you have a photon readout. Okay, so if there are no questions, I will now pass to the second kind of excitation that we studied, which are Magnus excitations.
Yeah, more or less you have 50 minutes.
Okay, yeah. So Magnus excitation, as I briefly mentioned before, are associated with spin excitation, so the spin of the ions. And in a generic material, the spin of the ions do not have a specific direction in the ground state, so they will be randomly aligned. But if you take some specific samples like ferromagnet, in the ground state at low temperature, all the spins will generally pointing in a specific direction. And these, in the simplest cases, can be schematized by an Heisenberg Hamiltonian. So for a ferromagnet, where J, which is the coupling, is larger than 0, all the spins will be aligned. And if you have an external perturbation, this can induce oscillations around this ground state. And magnons are just one of these oscillations. And just like for the case of phonons, this excitation will have both gapless and gapless branches. And if you remember again, the absorption kinematic requires that you are capable of coupling to the gaplet mode. So again, also for the case of magnons, of course, in reality, the situation is a bit more complicated. So first of all, even if you have magnetic ordering in the ground state, this does not imply that all the spins will be pointing in the same direction. So you have some kind of ordering, which is repeated in each magnetic cell, but this does not imply that all the spins point in the same direction in general. So before quantizing the system, you have to rotate to a reference frame, so to a coordinate system where all the spins point in the same direction. And once you are in this coordinate system, you can quantize the spin operators in terms of creation and annihilation operators. And now you can plug these expressions in the Hamiltonian and diagonalize the Hamiltonian by means of para-unitary transformation, which preserve the commutation relations of the operators. And you end up having the usual diagonal form where omega are the energies of this magnons mode, and then you have the creation annihilation operators. And for example, for the case of Higgs, this is the spectra that you get where gamma is zero momenta essentially. And you can see that you have 20 magnon branches in total, and these follow the general rule that for each magnetic ion in the primitive cell, you will get one magnon branch, one of which will be gapless, and this is associated with the broken rotation symmetry. Okay, and so how do you produce this magnon excitation with an axion field? So you start from the coupling to electron in the UV. You write this down in the non-relativistic limit, and this gives you a coupling between the axion wind and the electron spin. And you can map this to a coupling with the ion spin. The only difference going from the electron to the ion spin is this Landeggi factor, which tells you what is the fraction of the ion spin which is given by the electron spin. And typically, this Landeggi factor is close to 2. Okay, so and from this from this Hamiltonian, it's simple to express the spin of the ions in terms of creation and annihilation operator, and again, compute the rate for magnon's excitation. And you get something which is very similar to the rate, the expression is very similar to the one for phonon excitation, where again, the first part sets the signal intensity, while the second fixes the selection rules. And we will discuss these selection rules in the next slide, but if you neglect this for a moment, you can estimate the rate on resonance. And again, you see that for a kilogram-year exposure, you get a very good sensitivity to the axion to electron coupling. And I would like to stress this, in this case, you don't need any external field. So this is just the coupling of the dark matter axion wind to the electron spin that is giving you the signal. So independent of any external field. Okay, but in this case, the selection rules plays an even more important role than the case of phonons, because the general rule tells you that in the zero momenta limit, which is the one that we are facing, only the gapless mode can be excited, and that will be a problem because you cannot really match absorption kinematic with the gapless mode. And so you can understand these selection rules in a classical picture. So in the zero momentum limit, the perturbation will be almost constant over your sample. So all the spins are feeling the same strength of the perturbation. And because of that, they will process in the same way. And this means that this dot product does not change over time. And if you remember, the Heisenberg Hamiltonian only depends on these dot products, which are not changing over time. So also the energy of the system is not changing by the effect of the perturbation. And this means that you can only excite gapless mode. So this argument not only allows you to understand the origin of these selection rules, but also suggest you ways around this selection rule. So first of all, you could think to material which have non-degenerate Landé G factor. In this way, even if the perturbation is almost constant, and all the spin would see the same strength of the perturbation, the coupling of the perturbation to each spin would be different. So that the spins will process in different ways. So this dot product will not will change over time, so that you can couple to gapped modes. A second possibility is to have an external magnetic field. And this is the idea already exploited by the Cox experiment. So if you have an external magnetic field, this will lift the gapless mode in such a way that you can match the absorption kinematics. So the magnetic field introduces this extra term in the Hamiltonian, which introduce a gap in the gapless mode. And finally, you could think to an Hamiltonian which is not simply the Heisenberg one, so that the form of the Hamiltonian is more involved, and involves something which is not simply the scalar product of the spin, but it's a more complicated contraction of the spin. So in a way that even if this quantity does not change over time, you can still excite gapped modes. So of course we check all these classical ideas numerically, and you can see that indeed if you have one of these realization of your experiment, you can couple to gapped modes. In this plot, what I'm showing is exactly the constraint that you get exploiting each one of these three ways around the selection rules. So in pink, you have the case in which you have an external magnetic field, which will introduce a gap in the goldstone, and so that you can match the absorption kinematic. And you could also exploit this fact by changing the intensity of the magnetic field in order to have a small scanning of the axion masses, because varying the intensity of the magnetic field will vary the gap of the goldstone and also the mass of the axion you can match into. Then you have this orange and greenish line, which exploit an ideal material which has non-degenerate G factor. In particular, to obtain this line, we take the Higgs configuration and we tune the G factor. And finally, you have this NIPS3 line, which is exploiting a material which has non-homogeneous interactions. And you see that in all the cases, you get sensitivity to the axion line. I would say that this is a bit less promising than the phonon search, only in the regard that it's really hard to get a broadband coverage because you're only piercing through the QCD band exactly on resonance. So it's really hard to get a wide coverage of the axion mass. And of course, finally, I will tell that just like for the case of phonons, we show the constraint for different values of the resonance width, which you can have an idea of the order of magnitude of this width, but it cannot, we don't right now have a precise numerical value of this width. So for now, it's taken like almost a free parameter. So let me just conclude. So what we show is that phonon and Magnum's excitation can probe the QCD axion dark matter band in the 1/200 of milli electron volt region. And if you have a thoughtful choice of samples for the phonon case, you can get a broadband coverage of the axion masses in this range. And we identified 2 new ways to avoid selection rules in the case of magnons. And I would like to stress that, of course, a better knowledge of magnon and phonon line shape is needed to get more precise results of the reach, especially of resonance. And of course, we need a precise study of possible readout scheme. And so this will require some collaboration with experimentalists. So that's all. And thank you for attention.
Thank you very much, Andrea, for this very interesting talk. And it's time for questions.
Yeah, hi. So I would have a question on slide 28.
Okay.
So I
Yeah.
think the peaks, they belong exactly to the resonance, right? And even if you're not on resonance, you have a quite good sensitivity. So why is that? I mean, I would expect that you have similar peaks as in the plot on slide 48, where you show the G E coupling.
Yeah, they're exploiting. So the point is that you have less phonon magnons resonance to which you are coupling to. And I will also stress that even if you have good sensitivity off peak, the more you go away from the peaks, the less the more important becomes the approximation that we did. So we assume that you have a Bright-Wigner line shape, which is of course an approximation, which is totally fine on resonance, but the more you go away from this, the less trustworthy are the constraints. So you cannot really, like for example, extrapolate this to much heavier masses. Like if you really want to, for example, test this region, you can't really say, okay, look, we are of resonance, but we still have good sensitivity. You really need something which has a resonance more close to this mass range. And yeah, and the reason that we have less peaks in the Magnon case is just that we have less resonance to which we couple to.
Okay, thank you.
So maybe I have a question. Slide 48, when you show the reach in the axion coupling to electrons. So if I compare it to the reach of quarks, for instance, that uses that you also mentioned before, that is orders of magnitude less sensitive than white dwarf limit, for instance. So I was wondering, I mean, if you are over optimistic with this reach, or whether there is really a new detection concept that brings the sensitivity much down.
So. First of all, I think they are using less than 1 kilogram for the target, so that could lower a bit your sensitivity. And second of all, I think they are doing a step more, so they're proposing already a readout scheme. So they are using the coupling between the Magnon modes and the cavity mode. So they are putting their sample in a cavity and using the mixing between the Magnon's excitation and the cavity modes to read the signal out. And that also introduced a bit of suppression of the sensitivity. You get some suppression on the sensitivity because you take a hit from this mixing between Magnon modes and cavity modes. So both these effects lower a bit the sensitivity. And second of all, I don't really remember specifically what weight for the resonance they are assuming, because on resonance, your signal is proportional to 1 over the weight. So if you have a smaller weight, you have a better sensitivity. So you also, I should also check specifically what weight they are assuming for the resonance. So these 3 effects can change quite a bit the sensitivity.
Okay, thanks.
Can I actually ask a couple of questions?
Yeah.
Yes, please.
The first one is about this polaritons business. So this mixing with the photon, how does it happen? Meaning, so if you want, how do these photons look like? So what's the spectrum for them and stuff like that?
Let me go back.
If I understand correctly, the process is you produce a phonon, and then this phonon essentially oscillates into a photon for this small.
Well, yeah, the point is that you don't really produce a phonon. You produce these polaritons, which are a mixed state of phonon and photon state. So you have to, so once you have diagonalized this Hamiltonian, which is will give you the standard phonon excitation in your sample, you really need to do another step, which is diagonalize the Hamiltonian of the coupled system of phonon excitation and photon excitations. And when you do this additional step, you find that the physical states are not phonon, simple phonon, but you have a mixing of the two, and the true physical state are polaritons.
And these photons are the photons of the atomic electric field.
Yeah.
Okay.
And when you do this diagonalization, what you get is instead of having one transfer phonon excitation and one photon excitation, you have two polariton states. One of which is mostly photon-like, and one of which is mostly phonon-like. And so we will excite the mostly phonon-like state, but even this one has a small component of photon in it. And so you could think to use this fact for read the signal out.
I see. Okay.
Of course, I don't. So, to the best of my knowledge, there is no calculation to estimate what is the branching of this polariton state into photon. So you really need to know that to know how much the signal will be suppressed. Yeah.
Okay. Thanks. And I have another question actually, but this is my own ignorance about magnets. So if I understand correctly, the momentum that you would exchange to the system is very small. No, we're talking about milli-electron volts or even less, right?
Yeah.
And the magnet's interactions are not suppressed by powers of the spatial momentum?
Yeah. This is exactly the selection rules I was talking about.
Okay.
So for a standard material in the exactly zero momentum transfer limit, you cannot couple to the gapped mode. You can only couple to the gapless mode. So that you will have a huge suppression to couple to the gapped mode.
But even the gapless mode would be suppressed, no? Because in the zero momentum limit, their interactions are zero. I mean, as ghosts, I would say, no? Maybe I'm wrong.
Why so?
I mean, if they are ghosts, I would say that all their interactions must come with derivatives. So if you have zero momentum, they should go to zero.
Yeah, but the coupling to the gapped mode takes an additional hit of the momentum of the axion.
Okay.
So yeah, you have a standard momentum suppression, which is built in the coupling. But if you want to couple to the gapped ones, you take an additional hit just by the selection rules. And this will kill the rate unless you you circumvent the selection rules in one of these three ways.
Okay. Okay. Yes, I understand. Thanks.
Okay.
All right. Are there any other questions? Seems not. Then I wish to thank both Rico and Andrea for these two nice talks. And I'll see you next time.
Yeah.
Take care. Bye-bye.
Bye.
Bye-bye. Thank you.